In this video, I'm gonna explain to you the VC dimensions. I'm gonna talk about the basic definitions, but before we do this, I will start by motivating the VC dimensions. So, try to talk about why we actually care about these things. So, I'll just remind you that we are in the supervised machine learning setting where we consider some unknown target function f that maps from x to y. So an example of this could be x is r2 and y is 1 and 0. So this is binary classification. So we might have a data set of xi's and yi's. So these guys are two-dimensional vectors and these are 0, 1 labels. So then we could picture our data in a two-dimensional coordinate system. So this is R2. We could picture these xi's. Maybe they look something like this. And now I'm just drawing. Let's say zeros correspond to pluses, ones correspond to pluses, and 0 corresponds to minus ones. Then this could have been our target function. F could have looked like this, assigning plus above and so 1 above and 0 below. That could have been our target function. So what we want to do is we want to find some h that approximates f. So maybe we want to find a function like this. There could be an approximation. But to kind of capture what we mean by approximate, we define these two kinds of errors. We define the in-sample error and we define the out-of-sample error. So the in-sample error of some hypothesis is the sum over all the points. So could do a sum from is1 to n, and then we want the point-wise error on the ith guy. Right. So we want a sum for all points how much error is our hypothesis h making on the ith guy. So let's say we in this case want to use square distances, so then we could make the error be this guy. Okay, but so that's one immediate problem one realizes when one sees this. I mean, it would be easy to get in-sample error rate 0. You just let h remember the labels on all these guys and just return exactly that. Then you get in-sample error 0. And that's not really what we want. We want to learn the kind of general concept. So what we want to do is, if you get a new point that's distributed by the that comes from the same distribution as these points, we want to be able to predict well. And this is captured in the outer sample error rate, and the idea with the VC dimension is we get a nice bound on the outer error sample rate. We get that the outer error sample the outer sample error rate is less than the in sample error rate plus something, and this something in turn depends on the VC dimension of our hypothesis set. So hypothesis set is the set of hypotheses which we can draw h from. So this could be the set of all linear functions, or it could be the set of circles, or the set of convex polygons. So you could consider many different hypothesis sets. Great. So now let's see if we can arrive at the VC dimensions. So let's start by talking about dichotomies. Great. So if we have points, actually let's say we have some fixed sum hypothesis h. And let's say it looks like this. It's just a line. So everything above is going to be plus and everything below is going to be minus. Then if I have maybe x1, x2, x3, x4, x5, and say x6, then, well, h of x1 is going to be 1. Actually, let's do this with zeros and 1. So instead of this being plus 1 and minus 1, let's do this with just 0 instead. Then it also matches our label up here. So then h of x1 would be 1, h of x2, well, this would be 1, h of x3 would be 0, h of x4 would be 0, h of x5 would be 1. and h of x6 is again 0. So we see that we get a binary string of length in the number of points we get. So a dichotomy is basically the hypothesis H applied to say so that the given endpoints. So let's see, I just want to write it a bit differently so I have some more room. So maybe I just move this a bit up, get some more space. Great. So let's say that, well, so I apply my hypothesis on endpoints, capital endpoints. Then I get a dichotomy. So this is just a bit string of length n, capital N. So what if I did this for all hypotheses in my hypothesis set, and I kind of denoted this as a set. So I'm considering all dichotomies I can generate by my hypothesis set. Well, how large is this? How many elements could this set have? Well, I mean, there can only be 2 to the n different bit strings. So how many bit strings could I make? Well, the first guy could have 2 values, and the next guy could have 2 values. So it's just 2 times 2. So this gives 2 to the n possibilities. So the cardinality of this guy is going to be less than 2 to the capital N. Okay. So far so good. Now we're going to define the growth function. So the growth function is the max of x1 through xn of the cardinality of this guy. So why are we maxing? Well, I guess some intuition is we don't want the dependency of this guy to a single data set. So we just say for endpoints, well, what is the largest number of endpoints we can generate all the hypotheses, or all the dichotomies. So let me try to say it again. For endpoints, what is the largest number of dichotomies a hypothesis set can generate? Great. So just a little bit of notation here. Usually we write this part instead as, we just say we call this h of, we define this to be this thing down here. Great. So now I just need to say 2 more things. Then we have all the definitions in place. So we say k is a breakpoint if the hypothesis, the growth function of k, is less than 2 to the k. So we know that it's less than or equal to 2 to the k by this argument. But so basically if it's just not equal to 2 to the k, then we say that's a breakpoint. So k is a breakpoint if the growth function to k is less than 2 to the k. Okay, so then you should try to consider, well, is k plus 1 a breakpoint if k is? You should try to convince yourself that this is the case, and then follow on with the video, I guess. Great. So let's suppose you convince yourself that that is true. Then the VC dimension of H is the maximum capital N such that the growth function for n is 2 to the n. Okay. So it's kind of the largest number of points, x1 through xn, where we can generate all 2 to the capital N dichotomies. Great. So I think I want to do some examples now, and so I'll try to do these on the right hand side over here. Maybe if I can, having some problem with space right now. So let's look at an example, and let's say I consider the hypothesis set of circles centered at 0.0. So let's just try to visualize this. So what I'm saying now is, well, up here I could use lines. Now I'm saying, well, I can only use circles. So I could use stuff like this or this. Great. So if we can compute m of h, then maybe it'll be easy to see if there's a breakpoint for this and what the VC dimension of this hypothesis set is. So maybe let's consider just one point. So let's say I have a coordinate system and I have one point x1 sitting here over here. So then I want to make both labels. I want to assign x1 0 and I want to assign x1 1. So let's say that if a point is inside the circle, so let's look at this circle right now, then we say that a point is inside, we give it +1, and if it's outside, we give it -0. Okay, so then in this case, if we wanted it to have 0, we just have the little circle in here, and then, well, then we get this dichotomy. And then if we have the big circle around, we get a 1 because it's inside, and then we get this dichotomy. So then we conclude that mh of so this circle thing for 1 is 2. So then this is definitely not a breakpoint, right? It's mh of n is not less than, so 2 to the 1 is just 2, right? Great. So let's maybe look at 2 points then, make it a bit more interesting. So let's say I'm looking at this point and this point, x1 and x2. Could I make them all now? So let's say I have x1, x2, 0, 1, 0, 1, 0, 0, 1, 1. So clearly I can make 0, 0 again. I could just do like this. I could do the big circle here and get 1, 1. Now I could also make this circle in between. This will give me a +1 and a -1 here. So I'll get this guy. But so you can't really flip it and flip these two guys, so I won't get this. So in this case, the growth function of 2 is 3. And this is less than 2 to the 2. So then k equals 2 is a breakpoint following the definition up here. And we also see that the VC dimension of h, well, the largest value where we can compute all 2 to the n dichotomies, well, this is just 1. So the VC dimension of h is 1. So we actually see here that the minimal breakpoint is 1 larger than the VC dimension. And this is actually true in the general case. And you should try to think about that and convince yourself that this is indeed the case. Great. So I just want to take this example a little bit further. Oh shit. So let's see if we could reduce this. So it turns out that the circle, we could also think of the circle as if you're within the radius of Origo, then we say yes and else no. So it's actually only the distance to Origo that matters. So we could transform each point by computing the distance to the center and then just have them as points on a line. And then you can do the same thing. You can realize that if I want to generate all of these guys, so now my circles would just correspond to choosing some point and saying to the left of this it's 1 and to the right it's 0. Then I could again say, well, I could just put the guy here, so then I get this. I could put it over here, then I get this, and I could put it in here, and then I get x1 is 1, so I get this, but I can't make this guy. So the nice thing here is that if I add another dimension here, and I kind of consider spheres in 3 dimensions, I can do the same reduction. So then we also showed that for spheres, for like, then the breakpoint is also 2, and the VC dimension is also 1. And similarly, this generalizes to higher dimensions. So that's really kind of nice. It's also quite easy to see that in this case, the growth function, if you consider it as kind of as you have, if if you have n points here, then it's kind of easy to see that then, well, I can only make n plus 1 dichotomies. So the growth function as a function of n will be n plus 1. And I'm just gonna, maybe I'll need some more space here. So sorry for my order, I'll just continue up here. So what I said was that the growth function of these circles was n plus 1. So now I'm gonna show you what this something was in the beginning here. So E out is less than E in, and then the something is root 8 divided by n log for growth function of 2n over delta. Okay. Pretty sure this is what it is. I might be remembering it wrong. It's in the Learning from Data book by Abu. So it's on page 50 or something like that. So the idea here is, well, say I have some algorithm and I train on maybe let's say I train on 10,000 points, and let's say I'm using circles like before, and I have in sample error rate, say 0.04. So I have 4% error on my training set, and then we can compute this. So let's say, so the thing says that this here is true with probability 1 minus delta. So let's say we want the probability to be this thing. So then delta is 0.05. So then we could actually compute this thing over here. So we'd get 8 over 10 to the 4th plus log 4, and then the growth function, which is n plus 1, so this is 2n plus 1 divided by 0.05. Great. So this just corresponds to multiplying by 20, so we get 80, 160n plus 80. So you can compute this value, and then you kind of get a bound on the in-sample error rate. And that's the idea with the VC dimensions. So let's just recap. We saw some motivation for the VC dimensions. Then I promised you we would be able to bound the error rates. Then we defined dichotomies, we defined growth functions and breakpoints, and then finally the VC dimension. Then we saw an example, and finally I showed you in this example how I could bound the outer sample error rate given the in-sample error rate and this something term using the growth function. So actually I didn't really use the VC dimension here, but it holds that this guy is less than or equal to n to the power of the VC dimension plus 1. So if we didn't get an exact form of the VC dimension, we would have had an easy bound. It would have been well, we would get exactly this actually. So if we plugged in n to the 1, which is the VC dimension plus 1, we would have gotten exactly what we have up here, and then we would have gotten the same thing. So this is kind of a special case where we get the exact VC dimension. Sometimes it's a bit more complicated, and we are satisfied with upper bounds like this. So this is all described in the book on pages 50 to 55 or 60 or something, and I really recommend that you give it a read. Great. Thanks for watching.